Pop quiz time. How many joints are in an average humanoid robot? Okay, I'll tell you. Potentially over 70. And what does that mean? A whole lot of switches. And when you've got somewhere around 600 switches, you need to keep your dead time in check, you need to make sure your motors are operating efficiently, and you need to keep your inverter losses as low as possible. But how can we do all of that? With GaN technologies. That's how. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Eric Persson from Infineon and I explore why power is a key driver for efficient and reliable robotic movements, and how GaN technologies can help motor control solutions be more compact, integrated, and efficient. We also investigate the role of field-oriented control in humanoid robotic applications, and why the choice of GaN power transistors can make all the difference in your next humanoid robotic project. And before we get started, don't forget to click that link. There you can find even more information about this topic from Infineon. Hi, Eric. Thank you so much for joining me.
Amelia, great to talk to you again.
Excellent. Okay, so we're talking all about GaN solutions for humanoid robots today. So, Eric, before we get started, what all will we be covering?
We're going to talk about the robotic motors and actuators. And let's start with just making sure we're all on the same page for these kind of motors, the permanent magnet machines and how they work, the different commutation methods that they can use, and how that's controlled. Because all of that is important to then understand why are the power transistors important and how can they help given the type of motor and the type of control that we're going to be using. Then we'll look at the effects of going to higher switching frequencies and using different transistor types that will affect the size of the drive. It will improve torque ripple through dead time improvements. And then we'll finally put it all together and look at, all right, what are the total losses, not just the drive, not just the transistor, but the system, the motor and the drive together. That, I think, will bring it all together to show that all of these things together as a system work to improve overall efficiency and density.
Fantastic. So, Eric, power is a crucial component in these types of systems, right?
If you think about these robots, I mean, obviously there are all of, the sensors and vision and balance and thinking and lots and lots of control topics. And certainly power is one of them in order to have longer runtime, lighter weight, not have to be carrying around an enormous battery in the robot. You need a system that can efficiently convert the battery energy to mechanical power. So in some of those areas, like in this graphic, we use traditional silicon type of transistors for on-off control, enabling, disabling various systems where dynamic performance maybe isn't that critical. And that could be as many as 200 different power switches in a robot like this. Then there are kind of the more critical areas where you need the really high power density. So you need small drives with the ability to deliver high torque. And again, it gets down to making efficient use of the battery so that you have longer runtime, less heat, and all of that. At the end, I'll show you some integrated solutions that really put this together in the smallest possible form factor.
So, walk me through the details of these mechanically commutated brush motors.
We probably all learned this at some point in, EE 101, but I want to make a couple of key points about, this whole idea of commutation and density in particular. I'm sure you've all seen something like the graphic on the upper part of the screen here that shows two permanent magnets on the left and right of a coil. It's a single wire coil representation here. So this is the classic simple motor. We call it a DC motor because you can apply a DC voltage to it, and that mechanical cylindrical commutator takes care of switching the polarity at the right time. So you have a B field, the blue lines between these pole pieces, and then the wire rotates, that's on the rotor, and it rotates through an angle. Right now, let's say it's at, this would be 90 degrees. So when it rotates another 90 degrees, it will be at a torque minimum. So if you look at the torque graph right below on the left, the torque goes from a maximum down to zero. So you have 100% torque ripple on this basic machine. If the coil of wire is oriented vertically, you have no starting torque, no way to get it going. And so a common solution to this is you go to the middle of the page and you see essentially the same structure, but now you have a two-pole motor with two loops of wire. And now you can also see in the torque curve that I have a much smoother total torque from these two wires. So for a shorter period, instead of going 180 degrees, now we only go 90 degrees per wire. And so it's going from its kind of sweet spot of minus 45 to plus 45 degrees. Then it commutates to the next wire and so on. And then you can carry that even further to the right there. I'll show, 7 loops, 7 poles. And ultimately the torque ripple approaches zero as you go up to more and more poles. But the problem is it becomes impractical because, first of all, just mechanical commutators by themselves are noisy, both electrically and mechanically. They wear, they create arcing and sparking, as it commutates. And so for a number of reasons, brush motors, they're still used very widely today, but they're typically in low-cost applications like, toys and other type of consumer products. The other problem is that it doesn't make very good use of the available copper cross-section because at any given time, only one of these coils is energized and doing work. As you add more and more coils of wire, you have, proportionally less space to fit the wire, and therefore, you end up kind of limited by copper, and I can't get the torque and power I need along with that smooth torque. That's the trade-off.
So, Eric, what about the electrically commutated permanent magnet motors and how do they compare?
That's a big innovation that occurred, probably 40, 50 years ago as power transistors. It started with SCRs and thyristors. You can see this is now a cross-section of what we call an electrically commutated, and this is a permanent magnet motor and drive. Starting on the right, kind of this cross-section of the machine, the outer cylinder is the stator. The A, B, C there indicate the windings. For example, you have an A plus and an A minus at, say, the 1 o'clock and 10 o'clock position. And similarly, you have an A minus and A plus at the 4 and 7 o'clock positions. So that's all part of the A phase winding. And then you have the same thing for B, the same thing for C. And now, instead of using a mechanical commutator, notice that the permanent magnets are on the rotor. So we can easily connect to and use an inverter to steer the electrical signals to this machine. And by energizing these coils in a particular order, then we can create this continuous torque and pull the rotor around its full rotation. And by using all of these windings at the same time, or at least 2/3 of them at the same time, as we'll see, we get better copper utilization and therefore a smaller package to deliver the same amount of torque. Now, not every motor has to be designed this way, but this is the most common type that we see in these servo motor type of applications. What we're showing here is what we call a trapezoidally commutated motor. There are other types as well, including sinusoidal.
So, Eric, can you explain a little bit about the different methods here?
Yeah, this is kind of a simple chart comparing four electrically commutated motors, like we just looked at, what the kind of two different designs, trapezoidal versus sinusoidal, and then of that, there's even further commutation methods. So let's start with the first line, the brushless DC motor, BLDC, which, by the way, is probably incorrect. It was called brushless DC motor, even though it's truly an AC motor, because it was the first electrically commutated motor that competed in terms of performance with the traditional brush type DC motor. So that's why it's called brushless DC. It really isn't a DC motor. Side note of history there. So the waveform, as we saw in the previous slide, is trapezoidal, meaning flat-topped back EMF. And don't forget, the back EMF waveform also indicates generally the torque function shape. So these have relatively flat top torque over a certain angle, and then you commutate to the next and the next and the next as you go. Normally, when you're driving a brushless DC motor, you only energize two phases. I might have one inverter leg sourcing current, the second inverter leg sinking current. The third inverter leg isn't doing anything. It's waiting its turn. You get really excellent torque out of this. I mentioned the trapezoidal commutation that we already saw. And as far as the torque control, the low speed performance of these machines is somewhat more limited. It has torque ripple at low speed. I mean, it has torque ripple at any speed, but at high speed, you notice it less because usually the inertial load kind of smooths that out. It's a very efficient, low complexity algorithm. I mean, you're just essentially running PWM current limit and you commutate to the next phase, and there you go. Easy to implement. Now let's talk about the permanent magnet synchronous motor, which are sinusoidally commutated, and their back EMF would similarly, and the torque function would be sinusoidal. In that case, you're driving all three phases at the same time, and if you think of it that, the voltage, if you were to look at the low pass filtered voltage going to those phases, you would see three sinusoidal voltages as it rotates, and those would be 120 degrees out of phase. You do trade off a little bit of torque for this sinusoidal commutation. However, what you gain is really excellent torque ripple and control. You can have extremely smooth torque. This is why it's so good for servo motors, is that you don't have that herky-jerky kind of, commutation going on. It's just super smooth commutation at any angle, at any speed. Now, I can choose either traditional, what we call V over F control, in other words, just driving a sine wave into it, and you control the magnitude of the sine wave versus frequency, and you still get excellent, low speed torque ripple, but it's not as efficient at high speed. You can't extract all of the performance out of the motor at high speed. And it's a pretty simple algorithm, medium complexity. Now let's get down to the bottom line here, where this is what we're really talking about today, is using what we call field-oriented control, or vector control, it's sometimes called, where you still get the excellent low-speed performance, but you can now get not only great dynamic performance, but outstanding high-speed performance. It's the best of all possible worlds, but it's a little more complex to implement.
So we also need to talk about field-oriented control as well, right?
Yes. Let me just mention that because, as I said, it's vector control, sometimes called, or field-oriented control. It's a pretty cool concept where the strategy, rather than simply driving current into windings, you have two independent variables. The first is flux. It's essentially the direct axis current, I sub d. Think of it as, you already have a permanent magnet, right? So I already have axial flux in the machine, but by energizing the windings in a particular way, I'm able to either increase that flux or counteract it and decrease it. And when I do that, it changes both the torque constant, Ke, and the back EMF constant of the motor. So I can kind of change the characteristic of the motor, and independently, I can also control IQ, the quadrature axis current, which directly drives torque. So, flux kind of just is there, and I can use it to affect the overall performance of the machine. And I want to essentially have as little as I can get away with, in order to not be driving additional RMS current in the windings. And then the torque, of course, is whatever I need to achieve the mechanical goal. So using this field-oriented control, I get high efficiency, smooth torque, and I can get fast dynamic response. Moreover, I can change the flux and thereby get, you can do things like field weakening. I can operate at speeds beyond the base speed of that motor and that voltage, but I trade off torque. I can give up torque but go even faster, and vice versa. I can gain back that high torque at zero or low speed. And you can see in the block diagram on the left that this is not a simple system. And on the right, I won't go through all this, but you go through these coordinate transforms from, phase currents to the D and Q axis that we just talked about. And then you have to go from rotating frame to stationary frame and so on. And then finally, there's the modulation, the PWM modulator at the end. And here again, you can use different types of modulation. Most commonly is what's called space vector modulation, SVM, but there can also be others, third harmonic injection. There are certain two-phase approaches to simplify and reduce power and whatnot.
So, Eric, power transistors are a very important component in these systems. Talk to me about the role they play.
Yeah, so we've just seen kind of the refresher motor drive 101 here. So we looked at, the machine itself, mechanically commutated, electrically commutated, the different methods we can use, and all of that. And I think it's necessary because now it'll help you understand how the inverter, the switches driving voltage and current into the motor, help with improving these characteristics we want to improve, which is density, power density, and size and torque ripple and all of that. So we're talking here about, technically the term is voltage source inverter, and it's the three half bridges that you saw earlier driving our electrically commutated motor. In motor drives, turn on is almost always hard switching, meaning that turning on the transistor is forcing the voltage state from, one state to the other. There are losses associated with that, turn-on losses. And in some cases, you have to limit the DVDT, meaning that you have to slow down the switching, which can incur additional loss. I'll just mention here that that's mostly with higher voltage machines, like line-powered stuff where you have 300 or 400 volt bus or higher. And in that case, the DVDT is limited sometimes as low as like 5 volts per nanosecond, which sounds fast, but, with these modern fast switching transistors, it's possible to achieve 10 times higher than that. The problem is that in high voltage machines like that, the fast transients can cause corona breakdown or partial discharge, which leads to degradation of the insulation system. So in these 48 volt, under 100 volt kind of machines that we're talking about for humanoid robots, the voltage levels are typically low enough that we really don't have to worry that the DVDT is going to cause some sort of insulation problem. It might be an EMI issue, but that's not a reliability issue. On the turn off side, usually it's what we call ZVS, zero voltage switching or soft switching. And again, this is, especially with GaN, you can switch the channel off in single digit nanosecond before the voltage across it has changed at all. And now it's just the inductive current of that phase that gives you kind of a free soft switch turn off edge. So keeping in mind, our main goals here are we want efficient operation and we want small size or, high power density. And of course, the transistor has to be able to handle the appropriate voltage and current. What we're looking for in other characteristics are the lowest conduction loss. And here it's really just gets down to RDS on. Well, not just RDS on. That's, the Ohm's law portion of it, right? And more specifically, it's not just low RDS on, but it's fitting that into a smaller package. So low specific on resistance is what we call that in the semiconductor world. Low RDS on in a small footprint package. But when the transistor is during dead time between one phase turning off and the other turning on, sometimes you're in diode mode in these transistors, and you have effectively a forward biased diode, and that can be a much larger drop. We might be talking tens of millivolts, hundreds of millivolts when it's in the on state in the regular forward direction. In the reverse direction body diode mode, it could be volts. And I'll mention this again at the end because GaN has notoriously a larger diode drop than silicon, but we have a unique trick to solve that problem. I should also mention that having a short and linear, very predictable dead time without any intervening diode recovery also is important because it means that I can set my dead time to a very small value and therefore further minimize diode conduction loss. That's conduction loss. Now for switching loss, what we care about is typically charge. So not only the gate charge, QG, by having a low gate charge for a given gate driver, I can get very fast switching, even if I have a bunch of parallel transistors. And on some of these motor drives, you will see 4, 6, 8, 10, 12 transistors in parallel for the highest current drives. Also, the output capacitance, or the charge stored in the output capacitance, which is QoSS, helps to reduce the overall RMS current in soft switching when it's low, and the energy stored in that charge, the EOSS, every time my hard switch turn on, I'm dissipating that energy. So low EOSS directly reduces switching loss. Finally, minority carriers. In silicon transistors with the body diode, you have a finite reverse recovery due to the recombination of those minority carriers. It can lead to additional turn-on losses and increase EMI and the resulting voltage stress. And I'll show you a picture of that later on. Where GaN comes into play here is there are no minority carrier-induced QRR charge, which means lower turn-on loss and reduced voltage stress and less EMI.
So, Eric, what about using GaN solutions here? What kinds of benefits do they bring to the table versus silicon?
We just looked at all the things we want. The conduction loss, lower conduction loss, we want lower switching loss. So now let's look at GaN comparing to silicon. We just go down the list here on the left, lower specific on resistance, lower QoSS, lower QG, and so on. These are all the things that we're hoping for to come close to the ideal transistor for a drive. And not only that, but the package, these surface mount packages are very low inductance, which is important in being able to achieve these fast switching, low loss applications on your printed circuit board. If you have leaded packages, you're already running into problems because just the package inductance alone makes it difficult to switch quickly. In the highlight here in yellow, I mentioned Gen 5, which is our latest GaN technology, has a built-in Schottky body diode. We've done this in the past with silicon transistors, and it was always a big benefit for things like, buck converters and all of that. Here, this adds that benefit. Remember, I mentioned that GaN is notorious for having a relatively high voltage drop in diode mode by itself. Now, by integrating this Schottky body diode, it's not only being a Schottky, it's majority carrier only, so still no reverse recovery. And second, the Schottky contact has a much lower forward voltage drop than even the silicon. So you get the best of all possible worlds and kind of remove the final roadblock of why use GaN or not. At this point, it's a smaller device. It has lower gate charge, much faster switching, and now even a better body diode than any silicon. So what can you do with that? Well, we talked about the field-oriented control, and I can now go to higher switching frequencies with field-oriented control. Now, I know what you're thinking. Wait a minute, higher frequency, isn't that just going to increase losses? So the answer is yes and no. We're doing this for a couple of reasons. So it'll all come together in the end. Just stay with me here. We want to be able to increase the switching frequency. If you see the scope plots of phase current here, same control strategy and all that, but 20 versus 100 kilohertz. What you notice is that overall, the low frequency motor current shape is roughly the same, but the hair on the waveform there, which is the ripple current of the PWM, is much less at 100 versus 20. And that's the key, and we'll get into that in a little bit here to understand why this is an improvement. From the system standpoint, though, overall with GaN, we get from a higher power density, and I'll show you some reasons why. We get lower ripple current that I just showed you by going to a higher frequency, and the acoustic noise. Of course, 20 kilohertz is pretty much considered outside of human hearing range, but these humanoid robots are in the home with pets and other things that can hear up to 40 kilohertz. So being able to go to 100 puts the motor high-pitched noise outside of the hearing range of anyone in the household. And then also the other advantage of going to higher frequency are the control dynamics. By increasing PWM frequency, we can increase current loop bandwidth, and that leads to better, more precise control of the overall, whether it's velocity or position control. Let's now put this together and look at how can we reduce size and improve density using GaN going to higher switching frequencies. And again, I'll save the why are we going to higher frequency for losses for a couple more slides because it'll all come together at the end. On the left is a silicon inverter board switching at 20 kilohertz. And my criteria for the bus capacitor is that I need to keep my voltage ripple, and this is the voltage ripple due to the motor current, at less than 1%. If the ripple current increases, it means I have less available voltage at that minima, and therefore I can't drive the current I need. I can't get the performance I need. So I need a relatively stiff DC bus on the motor drive in order to get the full range of performance. With the 11 amp RMS motor current, in order to meet these conditions that are in the asterisk on the bottom here, I need an enormous aluminum electrolytic cap, 1800 microfarad. Why? Because these capacitors are rated for a specific ripple current. And on these, I'm really at the limit, even with these two big caps, because each is rated at about 5.5. So I'm right at the limit with 11 amps of motor current. And the reason is because it creates self-heating inside of the electrolytic cap and reduces performance. And you get losses, right? I mean, electrolytic capacitors are not lossless. So it's big. I'm going to suffer losses and they're going to heat up. Now I go to the right-hand side. I've gone up 5x in frequency with GaN, and we'll compare the switching losses a little bit later, but the thing is 100 kilohertz versus 20 isn't 5x more loss. Because I'm using GaN, I gain some benefit, a significant benefit just from that. But in this slide, what I want to focus on is look at the size of the capacitor bank. I've now shrunk these using multi-layer ceramic capacitors. It's gone from 21 millimeter total thickness to 3.6, right? And in this case, I can do that because the ceramic capacitors are much more capable of handling high ripple current. And I can achieve the same 1% ripple with only 88 microfarads, right? So I'm 20x smaller value of capacitance, and yet I can achieve the same ripple voltage because I'm operating at 100 kilohertz.
All right. So, Eric, earlier you mentioned shorter dead time. So, can we take a closer look at that as well?
Yeah, let's take a look at dead time. Now remember, I said that in the previous slide when we were talking about capacitors that one of the reasons we want the low ripple voltage is because if I'm losing a couple of volts on the cap bus, on my DC bus, I have less headroom. I'm not as able to drive the current I want. The same is true with dead time. So what is dead time? Just a reminder, in a given phase of the three-phase inverter, if I shut off, say, the upper transistor, I can't immediately turn on the lower side, right? I can't do it, half a nanosecond later. I need time to make sure that the transistor really has fully turned off. And there are also propagation delay variances between different gate drivers. So I need to allow a few nanoseconds, maybe 5 nanoseconds, just to make sure that the gate driver speeds aren't overlapping with each other. Then I can turn on the low side. If I don't wait, if I don't have a dead time, and I turn on the low side immediately, I'll get what's called a shoot-through, which is when both transistors are on simultaneously, creates a huge spike of current, it's lossy, it's hard on the transistors. You don't want to go there. All bad things happen when you have shoot-through. So now looking at this chart, I'm showing a dead time in gray of 300 nanoseconds, which is typical for silicon, versus about 6 times lower, 50 nanoseconds for GaN. And you can go even lower than this, but really there's not a big need. And this is showing motor phase current, all other things being equal. And what you see is, number one, I'm at a lower overall RMS current using the 300 nanosecond dead time because dead time is not productive, right? It's time spent waiting for the next switching action. It therefore reduces the applied voltage, and that's why you see that the current is lower. In addition, notice the crossover distortion, meaning that flat spot in the gray waveform around 0, and that leads to torque ripple. So you get less smooth commutating action, less smooth torque with longer dead time. All of these things we talked about earlier, we want smoothest possible torque and highest possible delivered power in a given package size. And GaN has that advantage because it can achieve these lower dead times on both counts.
So, Eric, motor losses actually decrease at higher switching frequencies, right?
Yeah, now you're getting to the heart of what we were talking about before. I mean, I remember when I was first discussing this concept with one of my colleagues, and they said, hey, we're going to 100 kilohertz on the motor drive. Now, in the power supply world, going from 20 to 100 kilohertz makes sense to me because my transformer gets smaller, my EMI filter gets smaller, and all these things. But in the motor world, my first thought was, well, wait a minute. All that's going to happen is the inverter losses are going to increase directly with frequency. So why would I want to do that? And here's the answer. When you look at the motor, there are hysteresis and eddy current losses you can kind of see in this diagram on the left. And hysteresis losses also go up with frequency, and eddy current losses go up with the square of frequency. But there's another component there, the B, which is the flux density. And when I reduce my ripple current, so when I go up in frequency, my delta I, the ripple current, goes down. And it goes down to the N power here, as you can see, compared to linearly with frequency. So the eddy current kind of balances out. The hysteresis losses go down significantly as you go up in frequency, all other things being equal. So let's look at, in this case, this motor running at 20 kilohertz versus 100 kilohertz, you can see the waveforms, and you can see how the 10 amps peak-to-peak ripple current drops to only 5 amps peak-to-peak. This means that the losses in the machine are actually going down. Now the question is, well, how does that balance out versus the losses in the inverter going up? So we run a test. It's the same inverter, it's the same motor, and the same test condition. It's a 48 volt DC bus, 380 watts of measured mechanical power coming out of the motor at 4,000 RPM. On the left is 20 kilohertz operation. Now this is GaN for both, right? I didn't switch silicon and GaN. What I want to show here is independent of the transistor, how just changing the frequency improves the overall losses. Things would be even worse if I use silicon on the left. That would be a bit of an unfair comparison. So we're trying to do level playing field. All I want to know is how does the motor efficiency change and how does the inverter efficiency change as I go up 5x in frequency. So we'll get to the overall at the end. Let's look at motor winding temperature. On the left, we're at 68, and on the right, it drops to 55. Now, that doesn't tell you much because you don't know how much loss are we talking about here. And in this case, with the motor spinning, you get windage, you get cooling because of the airflow through the motor. It's hard to tell what's really happening here other than the temperature went down at 100 kilohertz, okay? And similarly, the temperature of the drive, the GaN on the motor drive, and you can see that in the thermal image below with the same temperature scale for both. We went from 38 to 45. Now, this is at a room temperature 25 degrees C, so it's not very hot to begin with, right? It's a very small temp rise and it went up a little bit. What really matters here is if you go to the top line, the overall system efficiency, 89% at 20 kilohertz, 96% at 100 kilohertz. So if you do the math here and say, well, okay, what are the losses given my 380 watts of delivered power? I've got about 47 watts of total loss in the motor and drive on the left, and only 16 on the right. So I have a 3x reduction in total loss. So the motor is by far the largest loss here, especially here at the low frequency, and it's dramatically reduced by going to 100 kilohertz. That's why we go up in frequency, and even though the drive itself runs a little hotter, the overall system losses are substantially reduced.
So, when it comes to 100 kilohertz and 200 kilohertz transistors, Eric, how does GaN compare with silicon solutions?
200 kilohertz is probably pushing a bit high for this. I don't know that you'll get a significant benefit, but what this shows is that at either frequency, whether I'm looking at power loss or whether I'm looking at temperature rise, in every case, from lightest load to full load, there's a clear benefit. I mean, you could argue that it's a smaller benefit at 100 kilohertz. It clearly gets better as you go to 200, but even at 100 kilohertz, clearly a significant benefit in terms of power loss. So what I'm saying is, yeah, you could run silicon at 100 kilohertz and run your motor, but now that benefit is reduced significantly because my motor power loss went down, but the drive power loss is, substantially more. I think the other key takeaway here comparing silicon versus GaN is on the right-hand side where we look at the switch node voltage of each of these technologies under the same conditions. The green is silicon, and you can see it starts out with kind of a slope at around 10 nanoseconds. You can see it's starting to rise. You might be wondering what's going on there. That's reverse recovery, right? So what you're seeing here is that in that range around 10 nanoseconds where the GaN is still essentially zero or even slightly below, the silicon is already in this recovery where the high side's trying to turn on and it's fighting the recovery of the diode. Then it kind of abruptly heads up And then you can see kind of this change in slope right around 20, 18, 19 nanoseconds. The slope changes. That's where the recovery is done and the diode lets go. And you get this classic ringing and overshoot associated with, silicon diodes with reverse recovery. So, the ringing and overshoot, you can say, it's no big deal, but it can be because, number one, it's going to increase EMI, as I mentioned earlier, and the peak voltage is higher. Not a huge deal here, but it depends on your layout. If you compare to GaN in purple, very smooth, no ringing, no overshoot, just a nice smooth transition. That means that I don't have to use a 100-volt part here. I could use an 80-volt part. I could even use a 60-volt part if I wanted to. It depends on my comfort level on my bus regulation. But with silicon, I don't have that option. I mean, it's already hitting almost 60. I could maybe go to 80. So these are all considerations. It's not just about power loss and efficiency. It's also about EMI and conducted and radiated emissions. We can zoom in a little bit more on the next slide, 15. And again, here, this is just showing the two transistors in the bridge and their voltage. And you can see, if I'm looking at the yellow, which is the lower transistor that's turning on, it's at 48 volts. And then before the transition, you can see a little bump upwards to a little bit higher voltage. This is dead time, right? So the dead time begins right at that little bump up on the yellow curve. And the dead time then is all the way over to where it then turns on. And then you see the nice smooth voltage transition, no drama, no ringing, no overshoot, just a beautiful smooth transition down to zero. And conversely, the opposite transistor is just a mirror image of that. Again, this is one of the great benefits of using GaN is that the switching waveforms are very well behaved and it helps to mitigate noise and EMI problems.
Eric, what kind of benefits do GaN solutions bring to the table when it comes to overall motor efficiency?
As we kind of saw before, just summarized here, 16 kilohertz, depending on, how I do my modulation, or going to 100 kilohertz, I can almost entirely get rid of the ripple current. I'm left only with the motor phase current. And the high frequency ripple in the green there, you can see it goes from 4.2 amps on the left down to 2.5, down to 600 milliamps on the right, almost negligible. And lower left, we talked about how the motor losses are very strongly dependent on both frequency and the magnitude of the ripple current, which are inversely related to each other. And the good news is, as you go up in frequency, motor losses go down. And then you can see kind of the summary here of both efficiency and temperature versus load, and then of course temperature versus time, showing the benefit of how GaN helps to reduce temperature and improve overall efficiency.
So, reference designs can be really handy for these types of applications. Does Infineon offer any GaN motor drive reference designs for humanoid robots in particular?
There's a new design, the upcoming kind of an acronym jumble here. This is the Humanoid robot motor drive. It's a 48 volt, 25 amp rated reference design. So this is designed to operate over the range of 15 up to 60 volts. 48 is a typical. It can deliver 25 amps or more, a kilowatt, 99% peak efficiency at 100 kilohertz. You'll see a picture of it in a moment here. So don't forget, Infineon doesn't just make power transistors. All these little blocks here, we make the controllers and all the communication protocol, battery management. And then on this reference design, instead of discrete transistor with separate drivers, we're using an integrated power stage I'll show you in a moment. And we have different types of sensors, including lossless current sensors that use tunneling magnetoresistive technology to get very high bandwidth, high accuracy, low drift, low cost. They're great. Those orange boxes on the right there on the motor phase. And we have position sensors as well that you'll see in a moment. So yeah, we have all of these parts. Let me next move to the power stage, what that looks like. So if you look down the lower right, you can kind of see the block here. It's the high side and low side GaN transistor with an integrated driver, and it's got current sense with a 3% plus or minus typical accuracy, range of up to 60 amps. It has over current protection, over temperature protection, and so on, short circuit, under voltage lockout, pretty fast propagation delays, 20 to 30 nanoseconds, minimum pulse width of 10, and so on. There's a couple of different variants of this. And it's in a 4.5 by 7 millimeter package, really, really small. You can see some of the part numbers here. These are, if not already on the web, these are shortly going to be released. Along with, you asked about the reference design, and I show a picture of that on slide 19 here. This is the reference design. It should be, we're in March at this moment. This will be released in April. This has the power stages we just looked at. It has the current sensors and the controller, and even includes this TLV 5012B. That's the position sensor. So if this is mounted on the end cap of the motor, it can directly sense shaft position without any sort of intervening encoders, wires, and all that. It just directly senses shaft position. So it's a pretty cool design. This is a very high power level, highly integrated, 66 millimeters in diameter, delivering up to a kilowatt of power for these high density, humanoid robotic joints.
So, Eric, what would you like my audience to take away from today's Chalk Talk?
Well, I think we've seen these humanoid robots have very specific requirements. They need to be efficient and compact in order to fit the form factor and have a reasonable battery runtime. And using the combination of field-oriented control, higher switching frequency, and the GaN inverter, we can provide really exceptional performance, clean switching waveforms, low EMI, smooth torque, better than we can with silicon, especially at the same switching frequency. And don't forget, we have all these other products, critical components for high-performance robotic drives. I put a little QR code there you can scan for all of the products that are involved in humanoid robotic technologies. And just, to summarize that, silicon's great. We sell a lot of silicon today, but to get that extra measure of performance and highest density, longest battery runtime, GaN provides some significant benefits. And hopefully that was made clear in our presentation.
Excellent. Well, Eric, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia. Look forward to our next talk.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Infineon. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.